Hello, and welcome to episode 11 of the Kalopa Mission Control Podcast. I am your host, and it is a profound privilege to welcome you back to our quiet, observant corner of the maritime world. Whether you are listening to this while watching the morning light catch the dust motes in your kitchen, or perhaps taking a slow, solitary walk along a shoreline, listening to the rhythmic crunch of shingle beneath your boots, I invite you to take a deep breath. Let your shoulders drop and allow the frantic, breathless noise of the modern world to simply wash away. In a society that constantly demands our immediate attention, this podcast is designed to be a sanctuary of time. Here, we measure our progress not by the frantic ticking of a clock, but by the slow, eternal breathing of the tides. We gather to track the meticulous engineering of Kalopa robotics and to marvel at the vast, complex, and deeply beautiful expanse of our blue planet. The ocean has always been a master of keeping secrets. For centuries, its sheer, unfathomable scale has hidden both breathtaking natural wonders and the deepest of human impacts. Recently, a truly astonishing study was published by researchers at Global Fishing Watch, leveraging the power of artificial intelligence and satellite imagery to peer through the ocean's veil. By analysing over 2 petabytes of data from the European Space Agency's Sentinel-1 satellite constellation, scientists set out to map the true scale of human industrial activity at sea. What they found is both fascinating and deeply concerning. Between 72 and 76% of the world's industrial fishing vessels are not publicly tracked. They are operating as dark vessels, moving silently across the ocean without broadcasting their positions via the Automatic Identification System, or AIS. This hidden fleet is heavily concentrated in South Asia, Southeast Asia, and the coastal waters of Africa. These are regions rich in marine biodiversity, yet they are also hotspots for overexploitation. When 3/4 of the industrial fishing fleet is invisible to public tracking, it creates a monumental challenge for conservationists trying to protect fragile ecosystems. We cannot manage and we cannot protect what we cannot see. Yet, while human activity often hides in the dark, nature occasionally reveals herself in the most beautiful geometric mysteries. If we were to fly a drone over the shallow turquoise waters of the Sound of Barra, off the coast of Scotland in the Outer Hebrides, we would witness something that looks straight out of a science fiction novel. Scattered across the seabed are hundreds of giant, perfectly circular rings of pale sand, set against the dark green of the surrounding underwater meadows. Marine biologists affectionately call them seagrass donuts, though locals often refer to them as fairy circles. They are formed by common eelgrass, Zostera marina. While the exact mechanism that carves these perfect rings remains a puzzle, scientists believe it is a textbook example of a self-organizing pattern, a delicate dance of plant cooperation and competition, perhaps influenced by sediment changes or the natural dieback of older shoots in the center of a colony. These fairy circles are a beautiful reminder of the intricate architecture of marine life, but they also tell a more somber story. Since the 1930s, the United Kingdom has lost an estimated 44% of its seagrass meadows to wasting disease, pollution, and coastal development. These meadows are the unsung heroes of our climate, locking away carbon in their roots and buffering our coastlines against winter storms. Seeing these resilient, mysterious circles in the Sound of Barra is a poignant reminder of what we must work to restore. To truly understand the ocean's hidden wonders, we must sometimes descend far below the sunlit shallows. Late last year, a team of marine scientists aboard the research icebreaker Polar Prince set sail for the southern Newfoundland slope at the edge of the Canadian continental shelf. It was a race against time, pushing into the bitter end of the autumn weather window to explore a region of the deep sea that had rarely, if ever, been seen by human eyes. Dropping high-definition cameras 700 meters down into the pitch-black submarine canyons, the team discovered a teeming, vibrant world. They found ancient cold-water corals, some of which can live for centuries, growing at an extraordinarily leisurely pace of just millimeters a year. The cameras illuminated pink feather-like sea pens, bright red mushroom corals, and a bizarre, beautiful creature known as a lollipop sponge. These deep-sea corals are the speaking stones of the ocean. They carry within their skeletons a chemical record of the ancient sea. More importantly, they are the ecosystem engineers of the abyss, providing three-dimensional habitat and vital nurseries for countless other species, but they are incredibly fragile. For decades, industrial bottom trawling has scraped across these deep, unseen habitats, obliterating centuries of slow, quiet growth in a matter of minutes. The expedition to the southern Newfoundland slope is part of a desperate, beautiful effort to map these hidden ecosystems so they can be formally protected before they are lost forever. But how do we effectively protect these hidden spaces? We have learned that simply drawing a line on a nautical chart and declaring a space a marine protected area is rarely enough, especially when faced with the reality of dark fishing fleets. Increasingly, the most profound and effective conservation solutions do not come from top-down federal mandates, but from the deep ancestral wisdom of the people who live at the water's edge. In the warm, shallow coral reefs of American Samoa, researchers recently conducted a fascinating study on the populations of giant clams. These magnificent, colourful bivalves are deeply rooted in fa'asau, the Samoan way of life, serving as a vital local food source for generations. The scientists compared clam populations across different types of protected zones. What they found was a powerful testament to local stewardship. The highest densities of giant clams, up to 1,100 individuals per hectare, were not found in the federally designated strict no-take zones. Instead, the clams were thriving most abundantly in remote areas managed under traditional village enforcement known as fa'asau. When a community establishes its own closure terms through consensus among village chiefs, setting specific timelines and species restrictions, compliance becomes culturally internalized. It proves that empowering traditional community stewardship is often far more effective than imposing distant federal restrictions. Conservation works best when it respects and integrates the people who call the coast their home. We see this same beautiful principle taking root in the icy waters of the Canadian Arctic. Just recently, the Government of Canada and the Chikiktani Inuit Association celebrated the establishment of two vast new marine protected areas in Nunavut, Chikiktite and Sarvarjuak. These newly protected waters, which surround the Belcher Islands and stretch into northern Baffin Bay, provide critical habitat for narwhals, beluga whales and polar bears. But what makes this designation truly historic is the Sikulia Agreement, named after the Inuit term for the thin new layer of ice forming in the fall. This agreement ensures that the conservation of these waters is entirely shaped by Inuit priorities, knowledge and governance. It guarantees that the Inuit people will lead the stewardship of their ancestral waters, blending centuries of traditional ecological knowledge with modern conservation science. When we consider the vastness of these challenges, from tracking dark fleets across the Indian Ocean to mapping delicate seagrass fairy circles in Scotland to guarding ancient corals in the deep Atlantic, the sheer scale of the ocean becomes overwhelming. Even the most dedicated coastal communities cannot keep watch over the entire blue planet. This is the exact problem that Kalopa Robotics was founded to solve. If you were to step into our mission control room today, you would find the room quiet, the lights dimmed, and the primary telemetry screens dark. We currently have no active missions at sea. Our fleet of autonomous surface vessels has been safely recovered and is resting in the workshop. Their bright yellow hulls are dry, their solar arrays are being meticulously cleaned, and our engineers are deep in the process of running diagnostic checks on their internal circuitry. While our boats undergo their refits, it grants us a precious opportunity to step back and marvel at the sheer demanding complexity of robotic sailing and to acknowledge the vibrant community of innovators who share our passion. At Kalopa, our chosen vessel is the 2.4-metre autonomous sailboat. It is a machine shorter than a standard family car, powered entirely by the wind and the sun, designed to survive the most violent conditions the ocean can conjure. The development of this specific class of vessel owes a massive debt of gratitude to the Micro Transat Challenge. For those who may be unfamiliar, the Micro Transat Challenge is a transatlantic race for fully autonomous boats, aiming to stimulate the development of maritime robotics through friendly, yet fiercely unforgiving, competition. Running for well over a decade, the Micro Transat has a rich and varied history of teams that have taken part. University students, naval academies, and brilliant amateur engineers from across the globe have carried their small, heavily modified vessels down to the slipway, pushed them into the surf, and watched them disappear over the horizon, bound for the other side of the Atlantic Ocean. In previous episodes, we have discussed the physical endurance required to survive the violent, towering waves of a winter gale. But today, I want to reflect on the immense sensory and navigational challenges of the micro-transat. Imagine sending a 2.4-metre boat out into the vast open ocean. It has no human eyes to read the approaching squall line and no human hands to feel the subtle shift in the wind's direction. It must rely entirely on its onboard sensor suite and its programmed logic. During the micro-transat, teams sit in warm, dry laboratories, staring at computer screens, waiting anxiously for an iridium satellite ping that comes perhaps only once an hour. You watch the digital breadcrumb trail as your little boat navigates the complex swirling eddies of the Gulf Stream. The boat's wind vane must constantly measure the apparent wind angle, feeding that data into a microprocessor that instantly calculates the optimal trim for the rigid wing sail. The internal compass and GPS must work in perfect harmony to actuate the rudder, keeping the vessel on its bearing while compensating for the immense lateral push of the ocean currents. It is a continuous, exhausting mathematical dance. The history of the micro-transat is punctuated by heartbreak. Boats have suffered catastrophic sensor failures, their compasses scrambled by magnetic anomalies. They have drifted helplessly in the doldrums, their solar panels starved of light beneath thick, persistent cloud cover. But every single failure in the micro-transat has been a profound gift to the industry. It is a crucible of innovation. Through years of shared knowledge, the community has learned how to build redundant sensor networks, how to write power-saving algorithms that allow a boat to sleep during the night, and how to program a machine to patiently heave to and ride out a violent storm. The 2.4-metre Kalopa boats sitting in our workshop today are the proud descendants of that rich collaborative history. We build them small and we build them smart, because a boat that can autonomously navigate across the Atlantic is a boat that can change the future of marine conservation. Imagine a fleet of these silent, intelligent sentinels deployed to assist the communities we have discussed today. A Kalopa boat could be programmed to autonomously patrol the boundaries of the new Chiquiktite Marine Protected Area in the Canadian Arctic. Emitting zero carbon and making absolutely no engine noise, it could remain at sea for months. Equipped with passive acoustic hydrophones, it could serve as the unblinking eyes and ears of the local Inuit guardians, listening for the acoustic signatures of illegal fishing vessels or monitoring the calls of migrating beluga whales under the ice. Our vessels could sail slowly off the coast of West Africa, using advanced sensors to detect the presence of the dark fleets identified by Global Fishing Watch. By cross-referencing radar returns with AIS data, our robotic boats could instantly identify vessels operating without trackers, beaming their coordinates via satellite to regional enforcement agencies. They could serve as mobile laboratories, mapping the precise water quality and temperature gradients around the Seagrass fairy circles in Scotland, providing marine biologists with the high-resolution, real-time data they desperately need to understand how these delicate ecosystems are responding to a warming climate. These tiny robotic vessels are not meant to replace the passionate human stewardship of people like the villagers in American Samoa or the marine biologists exploring the deep-sea corals off Newfoundland. They are meant to extend their reach. They are the tools that will help us blend the brilliant ancestral wisdom of coastal communities with the cutting-edge data of the 21st century. To build a machine capable of surviving the open ocean requires a deep, abiding respect for the maritime environment. You cannot engineer your way out of the ocean's power. You must design a vessel that works in harmony with it. Our engineers spend their days obsessing over the waterproofing of a circuit board, the calibration of a wind sensor, and the elegant logic of a navigation algorithm. It is painstaking, deeply demanding work, but it is driven by a profound sense of purpose. The ocean is not merely an empty void to be crossed, nor a resource to be endlessly extracted. It is the life support system of our planet. It regulates our climate, it provides the oxygen for every second breath we take, and it houses a diversity of life that borders on the miraculous, from the giant clams resting in the shallow lagoons of the Pacific to the ancient brittle corals growing quietly in the absolute darkness of the abyss. As our understanding of the ocean evolves and as the threats against it multiply, we must evolve our methods of protection. We can no longer afford to be blind to the impacts of our actions. So, while our workshop remains quiet today, the work is far from paused. We are refining our code, we are testing our sensors, and we are preparing. Because when the time comes to launch our next vessel, we know that it carries more than just microchips and solar panels. It carries our collective commitment to watch over the waters that sustain us all. Thank you for sharing this time with me today. If you have enjoyed our exploration of marine conservation and the robotic technology we build to support it, please consider subscribing to the Kalopa Mission Control Podcast on your favourite platform. And if you know someone who feels that same inescapable pull toward the sea, I would be deeply grateful if you shared this episode with them. Until we meet again, may your horizons be clear, the wind be fair, and the seas be kind. Goodbye for now. Summary. In episode 11 of the Kalopa Mission Control Podcast, we explore the unseen wonders and hidden threats of the global ocean. From a recent AI-driven study revealing the staggering scale of dark fleets operating untracked across our seas, to the discovery of mysterious seagrass fairy circles off the coast of Scotland and ancient cold-water corals in the deep freezing canyons of the North Atlantic. We also celebrate the power of community-led conservation, highlighting how traditional village protections in American Samoa and new Inuit-led marine sanctuaries in the Canadian Arctic are proving to be the most effective ways to